Professor Haldane to come up on stage. So it's a TIFR tradition that our director says a few words at the beginning of these public lectures and then gives a memento of thanks to the speaker, after which I'll introduce the speaker. So I'd like to call upon Sandeep Trivedi.
Thank you, Kedar. So let me begin by welcoming Professor Haldane here in our midst. I know that he has been here before. He was here for a very exciting conference a few years ago. And allow me to add that it was an auspicious visit because he was awarded the Nobel Prize after he came to TIFR. So we can hope that this visit is also similarly auspicious and look forward to having him back in our midst. I also welcome especially all of you from IIT who are here. We have inaugurated a bus this time, which is in its first run this time, and I welcome you. I especially welcome our colleagues from BARC who are here in our midst. Thank you so much for coming. We had a very exciting lecture, as some of you know, from Dr. Srikumar Banerjee just before this one. And so it's really been a very exciting evening. I will not take up more time other than to say we have a number of outreach programs which involve public talks such as this one, and also involve a Chai and Wai series where we go out into the city of Mumbai twice a month to Prithvi Theatre and to Ruparel College. Those talks are given by some of the leading scientists in TIFR, some of our students, in many cases distinguished visitors we get. And if you can't catch the talk live, the talks go on YouTube, so I invite you to get on to the web and hear them there and engage with us and keep coming back. So a warm welcome to you all. And with that, I think I hand over back to Kedar. There's a small memento which I can give.
So it is now my pleasant duty to introduce Professor Haldane to you formally. He is not somebody who needs much of an introduction, but let me just say that he belongs to an almost unbroken line of Nobel laureates, of which he is the fourth. It starts with a prize in the 40s to Bridgman, followed by Van Vleck, followed by Phil Anderson, and then Duncan Haldane. And so, the joke is that the pressure is now on his students. So anyway, Professor Duncan Haldane is the Sherman Fairchild Professor of Physics at Princeton University. He's also the Distinguished Visiting Chair at Perimeter Institute. He's extremely well known in the physics community for his insightful reformulations of many, many things in physics, bosonization, how to think about the quantum Hall effect. He's most famous for his discovery of an even-odd effect in the physics of spins that form a certain set of spin chain compounds. And that goes under the well-known name of the Haldane gap. But he might tell us a little bit about that himself, so I won't belabor that. He is also extremely well known for his enthusiasm in communicating physics, especially in one-on-one discussions. And I am sure some of that will come through today when he talks to us about new developments in quantum mechanics. So with that, I'd like to welcome Professor Haldane.
Okay, thank you. It's a great pleasure to be back here at Tata Institute. I've been here at least, I think it's my third time. And I'm going to tell you a little bit about some of the kind of cool things that have been happening in quantum mechanics recently, and especially entanglement, which is this weird property that's at the heart of current ideas for having a new kind of quantum computers. Okay, so quantum mechanics has been around for a long time. So the laws of quantum mechanics were established way back in the period 25 to 32, and they're the heroes, Heisenberg, Schrödinger, Pauli, and Dirac. And the laws have stood the test of time. They haven't changed at all. All the tests of quantum mechanics to date have confirmed they're correct. So no one has made their career by betting against quantum mechanics. But it's, of course, a strange and kind of often scary thing, quantum mechanics, for people learning physics. And in fact, physicists themselves don't really feel they completely understand quantum mechanics and all its implications. But just because we know the laws of quantum mechanics really doesn't really mean that we immediately know everything that's possible that they allow. And there's an interesting comparison with laws of electromagnetism that way back in, 1864, Maxwell finished the last of the laws of electromagnetism. They've stood the test of time. They haven't changed. There's a story that Gladstone, who was later the prime minister, I think he was the finance minister at the time, he asked Maxwell, he told him, this is all very interesting, but is this useful for anything? What's it good for? And Maxwell was to have replied, he couldn't say, but he was sure that one day it would be taxed. And of course, it's taken quite a long time since then for all the possibilities to be discovered in electromagnetism. And of course, it's melding with quantum mechanics in lasers, but in fact, even in standard electromagnetism, it's still a very active area with new discoveries. For example, in the recent 20 years or so, we've discovered this whole new field of photonic crystals, which was really not there before. So it's still an amazing area which is vibrant, because they're the equations, but just looking at those equations, you can't really tell what they do. Okay. So starting around 1980, there was kind of new insights into quantum mechanics started to emerge, and this is when we started to find these new topological of matter, which I'm going to talk about. And also a little bit earlier, in the late 50s, Feynman, I guess, started thinking about what would happen when I start to make devices which start to get down to the atomic scale, where quantum mechanics, of course, is dominant. And this is really the origin of quantum information theory. The idea of quantum computers has probably started with what Feynman was thinking about. He gave a very influential talk called There's Plenty of Room at the Bottom, which is a play on, I think there was a controversial play called Room at the Top around that period. And so this has actually come together with all these new developments, experimental developments in condensed matter and quantum states, to kind of come together and be blended into this whole new way of thinking about quantum mechanics. And so what we're now aiming to do is not really take quantum states and measure them, which means basically breaking them, but to actually obtain a kind of control over quantum states, to kind of nudge them gently in a way that preserves information content of them and manipulates them without really hitting them with a hammer. And so actually many people think we're in a kind of new phase of quantum mechanics, which you could call a second quantum revolution, if the first quantum revolution was the one in 1925 to 32. And I think we're going to learn a lot from this attempts to manipulate quantum states in a gentle fashion. And I believe new technologies are going to come out of this. And of course, a lot of money is now being put in by both companies and governments in the hope of doing this. So anyway, the key message will be that as we understand quantum mechanics better, new and strange possibilities for the materials of the future and the technologies that they allow are emerging. And as I say, this new understanding has emerged from a series of unexpected discoveries. I mean, all the best discoveries in science are really kind of unexpected, because you can't get up in the morning and say, okay, look at your agenda and say, today I'm going to discover something big, right? So in general, this kind of curiosity-led research that people go in funny directions like ants scurrying around looking at all the interesting things, and occasionally something truly amazing shows up by this kind of process of diffused understanding of things. So what's quantum information? Well, classical information is stored in what's called a bit, which is basically a switch which is either on or off. And a classical bit then you can view as a little magnet, lump of lots of atomic magnets. Okay, I can't see the, this still working? I think the pointer is faded off, right? Got a new pointer? Okay. The quantum information is stored in a state of a single spin, but the classical thing is a whole lot of spins, all up or all down, and the switch behaves classically. Is anyone, maybe I can get a new, let me get one here. Is it working? Okay, good. So as I say, the switch is just on or off, but the quantum state of a single spin, which is really any quantum system which has just two states. So a spin is something that can be up or down, or in fact we'll see sideways, right or left. But any system with just two states is equivalent to a spin. We now call it a qubit, and it's parameterized really by a three-dimensional arrow that can point anywhere on the direction of a sphere. So there's clearly a lot more information in the state of the spin than there is in this switch, which is up or down. But the spin can only be, the direction of the thing can only be measured along some axis. So it's more information, but it's trickier to get in and out, okay? So anyway, the central theme in this whole new approaches to quantum mechanics seems to be this strange property called entanglement. And entanglement used to be just a kind of philosophical issue that people arguing about quantum mechanics would bring up. There's issues about, is quantum mechanics compatible with free will and things like this. These are very kind of philosophical questions that may be interesting, but they don't actually get you anywhere as far as technology and things are concerned, right? So the entanglement is actually now recognized as the central property of quantum mechanics. And Einstein first pointed it out, and I'll say, but now it's viewed as the fuel, rather than a philosophical question, it's actually now viewed as the fuel which will drive this possible new future quantum technology of quantum information processors. And what was Einstein's contribution? Well, Einstein is famous for the statement he made about the cosmological constant, which he added to his gravity equations to keep the universe static. But shortly afterwards, the expansion of the universe was discovered by Hubble. So Einstein called that his greatest mistake, but then now this dark energy has been discovered, and people actually think this is, a possible explanation of dark energy is indeed Einstein's cosmological constant. But in any case, Einstein's mistakes have always been very great and very instructive. So he brought up entanglement because he pointed out that quantum mechanics predicted it, but he felt it was so crazy it just had to be wrong, so that when the measurements were carried out, it would surely dispose of quantum mechanics and show it was only an approximation to a more fundamental theory which had local realism. And he actually called entanglement spooky action at a distance, his famous phrase. It's actually spukhafte Fernwirkung. I guess he spoke German, not English. But Schrödinger called it a much more neutral name, entanglement, or Verwicklung, I think, Verschrankung in German. And it's stuck now. So what is... Well, let's look at basic properties of quantum mechanics. I listed these kind of heroes of quantum mechanics, and one of them is Pauli. And one of the fundamental properties of quantum mechanics is the Pauli exclusion principle that says, basically, it says something like two electrons can't be in the same place because they have a property which is called fermions. And in fact, it's because of the fact that the electrons can't occupy the same space is that why we don't fall through the floor. You know, the reaction force, the force of the floor on my foot, Newton just said that was the reaction force without worrying where it came from, but what it actually comes from is the quantum mechanical Pauli principle, which prevents the electrons in my shoe from occupying the same space as the electrons in the plank of wood. And of course, the atoms themselves, as you probably know, are 99% empty space. So what is exactly this reaction force? It's precisely the Pauli exclusion principle. Well, oops. But on the other hand, we're built out of the things that hold us together, the ordinary matter which we're made of, which is such a small part of the matter in the universe, apparently. We're actually glued together by the chemical bonds that hold the atoms together to form molecules and make us. So it's a chemical bond. It's really a place where two electrons are somewhat occupying the same place halfway between two atoms or ions and gluing them together with the electric force, neutralizing force. But how do they do that because of the Pauli principle? It's because they actually have electrons have an additional property which is called spin. And they can be viewed as well as having a charge, they have this spin, and they can view them as a little like a spinning top. And they have the direction of the spin is a degree of freedom of the electron. So how the chemical bond avoids the Pauli exclusion principle, because the two electrons that go in the chemical bond have to have opposite direction spins. So that they're not in the same state, even though they're in the same region of space, because of this property of the spin. And the electrons are fermions, which mean that if you describe them quantum mechanically, the system has to change sign if I switch the two electrons around. So the quantum mechanical description of this is not saying that electron number 1 is up and electron number 2 is down. It's saying that half the time electron 1 is up and electron 2 is down, and the other half of the time electron 1 is down and 2 is up. And so this is this, oh, thank you.
Just a pointer, you will need that for the slide.
Okay, yeah, that's better. So, so this is the quantum mechanical state of the two electrons, and this is what Einstein worried about. So it's a mixture of up, down, and down, up, and it's minus. There's a minus sign here because if I switch the two around, this quantum mechanical wave function has to change sign. And this actually is the poster child for the maximally entangled state of two electrons. So actually, we're built out of entanglement. So what Einstein worried about was, suppose I take this chemical bond and stretch it, keep on stretching it so it's big. So does this really mean that if the chemical bond is this big, the electron here is half the time up and the other one is half the time down, and vice versa? And even worse, once you measure the direction of the electron spin, you fix it. So he would say, he was worried about thinking, if I measured this electron, found it was up, that somehow means that the other electron has to be down. And he worried, does that mean that some information about the measurement had traveled faster than the speed of light? It seems like it's incompatible with his notion of relativity, where nothing can travel, information cannot travel faster than the speed of light. In fact, there's no actual violation of the relativity principle here, because you cannot transmit information by this thing. It's somehow that, but it's certainly true that if the two people do experiments, they do the measurements, and then they get together later and compare results, 100% of the time they will discover they got, whichever result one got, the other one got the opposite result. And there's a more subtle thing, you can choose which direction to measure this spin along, and then there's a more complicated issue about what happens then. So anyway, he worried about this in quantum entanglement. It's kind of okay if it's on this atomic scales of the chemical bond, but one's on the moon or Alpha Centauri or something. How can this possibly be true? And in fact, in 1935, I presume nothing much was happening that day, like no country had been invaded or anything. Because Podolsky, his collaborator, went to the New York Times and told them that Einstein has demolished quantum mechanics. And apparently, actually, Einstein was very angry and never spoke to him again because he felt physicists shouldn't be washing their dirty linen in public, right? But anyway, this was the page one headline in May the 4th, 1935. Einstein believes he attacks quantum theory. But anyway, as I said, Einstein's mistakes, if they are mistakes, have been very fruitful because this led to various things. So Einstein posed this paradox called now the Einstein or EPR paradox, so the Einstein-Podolsky-Rosen paradox. And now we have EPR pairs. EPR pairs are these things which are separated for large distances while maintaining their entanglement. So the other people kind of sharpened up Einstein's arguments and discussion on this, and principally John Bell, I think, made the deepest analysis. And actually, long after Einstein died, by 1982, the experiments that he wanted to be carried out were carried out, and I guess the Frenchman Alain Aspect claims to be the first on that. But anyway, they did experiments, and quantum mechanics, of course, passed with 100% grade, because otherwise I wouldn't be telling you this, right? So the quantum theory is 100% correct. There's still some issues about the whole free will issue. You know, in Bell's thing, the experimentalists actually decide after the electrons are separated which direction to measure in, and I guess the only get-out clause is that nothing we do, we may think we're making choices, but it was all preordained. So that gets back to this whole free will issue. But on a practical level, we're now using entanglement, and we don't really probably worry about the philosophical implications about the whole thing. But the problem is entanglement over distances larger than the chemical bond is very, very fragile. It's fragile against what's called decoherence, that the electrons, which have this very quantum mechanical state, which is entangled with each other, become entangled with the environment and lose their coupling to each other, and the information that's stored in them is kind of diffused and lost, and that's our principal problem. So Aspect's experiment was not actually done with electrons; it's done with the states of polarization of light. Again, any two-state system has this is equivalent to a spin, and light can either be linearly or horizontally or vertically polarized, which is what your sunglasses are used to screen out the horizontally polarized light reflected from the road on a hot day. But something more like the spin is actually circular polarization, which can be right or left-handed. And first, the EPR experiment was carried out under Lake Geneva, and then it's been done because fiber optic cables allow photons to travel essentially unimpeded for large distances. It's been done under oceans, and in fact, China has made a big deal out of this because people at Hefei and USTC and Hefei have apparently made entangled states with a satellite, right? So, okay. So entanglement is now established. So where's this part of the story? In 1980, the condensed matter physicists, people thought they understood everything. Physics go through this period where, just before quantum mechanics was discovered, people felt in the 19th century that they knew everything, right? Almost. A little problem about atomic spectra and the spectral lines of light, but most things were under control. Similarly, around 1980, condensed matter physicists thought they had a basic understanding of electronic and magnetic materials. And actually, around that time, two kind of weird things were discovered, which didn't apparently have any kind of a connection at the time. One is this spin chain business, which I was involved in, and the other, more significantly, is the quantum Hall effect, which Klaus von Klitzing discovered. This was a theoretical discovery initially, confirmed experimentally, and this was a experimental discovery that took quite a bit of time to understand theoretically. But they turn out to be different because they they're new states of condensed matter where, unlike the previous things that we'd studied, the entanglement properties play a fundamental role, not just a minor role. And in the past decade, many, many more kinds of this topological quantum matter is discovered, and then it was pointed out that possibly a route to avoiding decoherence in quantum computers could come out of these things. So it's accelerated the excitement about this, and that's probably why the Nobel Prize was awarded at this point, not because of the early discoveries, but because of what those discoveries have, what other people have built out of those discoveries, right? You have to wait a bit of time to see whether something is really amazing or not. If it's really amazing, it's because you see that it's led to all kinds of new things after that. Okay. So as I say, this was the thing. This unexpected properties led to this prize, but they also led to this proposed platform for topologically protected quantum computing. So what's topological matter? It differs from ordinary matter because it has these properties, which we now can say actually entanglement properties, that can be described by whole numbers, like integers, like 1, -1, 2, -5, etc. So the basic issue is that states of matter which have a description in terms of whole numbers, they can't smoothly change into each other, right? You can't turn a knob and go smoothly from 1 to 2. You have to jump at some point. There's either 1 or there's 2. And that means that there's always something interesting at the boundary between a region that can be classified, for example, a boring number like 0, although 0 is actually a very interesting number, so I shouldn't say boring, but and a topological number, maybe -2. There's going to be a boundary from 0 to -2. And it turns out one of the hallmarks of the topological systems is something interesting occurs at the boundary, often. And it turned out that since no one had suspected there was such a property, they actually had topological materials sitting on laboratory shelves for many years. And people had done all kinds of huge computer calculations on their bulk properties, but no one had thought there'd be anything interesting. No one had looked very closely at their surfaces, and so it's only when you know something out there. So if you don't know it's there, you're not going to go looking for it. And once it became clear it was out there, people started finding topological states quite widely. So it's a really important property that the topological properties of materials can't change continuously. So today's kind of computer technology requires this very high, very clean silicon wafers that are grown in these ultra clean rooms, because one little speck of dust or hair or something falling on the chip will make it worthless, right? So you have to go to extraordinary measures to have clean rooms. But actually, since the topological properties can't change continuously, that means that a tiny amount of dirt or something can't change that. You have to do a significant amount of damage before you lose the topological property. And that's a very interesting contrast to the usual ultra-clean systems. So anyway, topology is also a mathematical subject. And it starts off as a classical example in mathematics is the classification of closed surfaces by what's called a genus, which is just a fancy name for the number of holes, or it's actually 1 minus a number of holes, I think, right? So a shape like a sphere has 0 holes, and you can turn a rugby ball into a soccer ball by squeezing it, or vice versa. You can deform the shape of the ball, but it hasn't changed its topology. To actually change it from a ball with no holes to a bagel or donut which has 1 hole, you have to do a significant damage to it, like to actually poke this hole in it. And of course, holes come in whole numbers, right? There's no such thing as 0.36 of a hole. So it's a kind of much more clean kind of measurement than measuring a length or something. So anyway, actually the topology started out with this great mathematical discovery by the great 18th and 19th century mathematician Gauss. So Gauss discovered all kinds of important things in mathematics. But actually the thing he discovered, which he thought was the most interesting of all his discoveries, he called it a fancy Latin name, his amazing extraordinary theorem. He discovered something that well, high school children will kind of learn this in school. Probably you have to remember formulas from geometry, and some of you at least will remember that the surface area of a sphere is 4 pi r squared, where r is the radius. Well, a sphere is a curved surface where the curvature is constant at every point, and there's something called the Gauss's curvature. You can actually inscribe 2 circles around the sphere, and they, at any point they have equal radii. So the Gaussian curvature is 1 over r squared for a sphere. And if you integrate the surface area of the sphere as 4 pi r squared, if you integrate the Gaussian curvature over the surface of the sphere, you have 4 pi r squared times 1 over r squared, which is 4 pi. And the formula is actually 1 minus the genus, or 2 pi times the Euler characteristic. Okay? But this is trivially true for a sphere. You can sort of do it quite easily in high school. You learn how to do that. It's less trivial to do for a rugby ball. You could probably do that if you're a smart kid in high school. But it's also true for a banana, right? It's true for anything with no holes in it. So I can bend this thing around. As long as I don't put a hole in it, the curvature can vary wildly over different parts of the surface. But when I add everything up together to do this integral, I'm always going to get 4 pi. And so this is the thing that the people who announced the Nobel Prize were trying to explain it to the public to answer these questions of what's it good for, etc. There was a large explanation in terms of coffee cups and bagels. And in fact, this whole coffee cup and bagel thing is the thing that experimentalists in this area just love, because experimentalists get a huge kick out of seeing something on this crystal they're measuring and might have something to do with mathematics, you know. So if you go to YouTube, you can see a picture, a movie of a coffee cup turning continuously into a donut and back again. And basically, you can count this. So there's one handle to the coffee cup, which is like the hole in the middle of the donut. If you look carefully, the curvature on the outer part of the bagel is the two radii of curvature are both in the same direction, while on the inner part, the 2 radii of curvature are the opposite part. So the integral for the bagel is exactly 0, because the regions of positive curvature on the outside part exactly balance the regions of negative curvature on the inside part. And then you can go further. You can have this object, which was explained at the Nobel Prize announcement. They call this a Swedish pretzel, which doesn't really exist. There's something called a Santa Lucia bun, but when they actually cook it, the holes get filled in. So it's a fake one. Well, this thing is called a loving cup, right? It's got 2 handles. Well, actually, this is the one. This is a real pretzel, the German pretzel, as they called it. Well, here's this weird thing, which I'm not sure what it's called, but I've heard people suggest it should be called a California loving cup. But actually, it's not as rare as that, because I managed to acquire a couple of these things. So But here's another one. I guess this is from a game called Portal. It's got a kind of hole through it. This one I had to think about. You have to kind of move the handles around. But after a little bit of thinking about this one, I realized it also has this has genus 3, because it's got 3 handles. This one has genus 3 too, but it's a lot more complicated. You have to, because of the hole down the middle. So anyway, so coffee cups, the boring coffee cups that all the experimentalists use, which only have genus 1, you know, you can find much more interesting ones around for topology demonstrations. Anyway, so, oops, sorry. So as I say, mathematicians like to make things much more abstract and much more general, right? And in fact, around 1944, the American-Chinese mathematician, I guess at Harvard, Chern, he generalized this theorem, which is called this is actually called the Gauss-Bonnet theorem, because Gauss never got around to actually publishing it. But Bonnet, or he didn't give the details or something, and Bonnet wrote up the details, so it's now called the Gauss-Bonnet theorem. So Chern made this thing much more. He generalized it from actual curvature of real surfaces like bagels and donuts and rugby balls to a much more mathematical, abstract curvature, and the genus got converted to the Gauss the Gauss characteristic or whatever. So, but this is a much more abstract algebraic version of the Gauss-Bonnet formula, which applies in this much more generalized context of curvatures. And actually, the mathematicians don't have a Nobel Prize. It's supposedly because Nobel's wife had an affair with a mathematician, so he was prejudiced against them. And they have this thing for young people. There's this thing in mathematics. They have this ageism that says if you're over 40, you're over the hill. So you can't get the Fields Medal if you're over 40. But then they introduced a couple of medals. The main one being the Abel Prize. But this one, the Chern Medal, anyway, it's got the Chern formula on the back. Another major math medal. So anyway, how's this got connected to anything? Well, around 1981. I discovered that a spin-1 magnetic chain had a novel state that we now actually, of course, understand to be something like the hydrogen atom of topological matter, the simplest possible example of these topological states. So spin-1 just means that the spin a half means a single qubit. For various reasons, it's labeled a half. So if you have two of these elementary spins pointing in the same direction, that makes spin 1. And a magnet, the usual kind of magnet that picks up paper clips, all the atoms have their magnetic spins pointing in the same direction. So they kind of will pick up the paper clip. But a much more subtle kind of magnetism called antiferromagnetism is that the atoms are alternatively pointing up or down. So you can't pick up a paper clip with this because the magnets are all opposing each other. But you actually can see it if you do experiments with neutrons scattering on crystals, and you actually can detect this thing. It's a kind of magnetism called the Néel state. So the way people envisage magnetism, and it's certainly a good picture in 3 dimensions or even 2 dimensions, is it's just an assembly of magnetic atoms. You just bring them together and have if it's ferromagnetic, all their spins are pointing in the same direction. Antiferromagnets are alternatively up or down. And there's a choice of direction they could point. They could be pointing upwards and downwards or right and left or whatever. But there's no particular, you could make this thing by just bringing these atoms and assembling them, just putting them together. There's nothing special coupling them. Well, entanglement, on the other hand, there's some kind of state that if I, basically in an unentangled system, if I make a measurement of the properties of this atom here, it won't affect the measurement of something here. But entangled things, if they're entangled, if I measure one half of it, it's got an effect on the other half, okay? That's the notion of entanglement. And it turned out what I discovered is actually best represented in this way. We'll see in a minute a picture of this. And one thing you see is that these kind of spin 1s, which are made of 2 spins, they kind of separate into 2 parts and kind of join with their neighbors, and you've always got one guy left over at the end. And that's actually very typical of these topological states, because this is a topological region. If there was something out, if I put some of this stuff on the other side, there'd be a kind of something left over at the boundary, okay? And as I say, this was actually a surprise, and it shocked the magnetism community. I mean, it was very good for me in the finally. This shows you that kind of new things often encounter resistance, which is good because lots of new things turn out to be nonsense, right? There were like reports of neutrinos traveling faster than light a few years ago, and then something called B modes in quantum gravity and all kinds of stuff. So lots of new things are wrong. Anyway, this was counter to the common understanding, and it was kind of initially denounced as nonsense, and my papers were rejected, I think, 3 times before it was published, or it was published on the 3rd time or something. But actually, you know, science is great in the sense science is not really a matter of opinion, right? There's a judge of experiment around the place, right? And it turned out that, you know, although I didn't understand why this state was so special, it was. And in fact, clever material scientists got challenged by this whole controversy, and you know, both theorists came up with lots of interesting new theoretical techniques to investigate the thing. So the controversy was actually very useful because it generated all kinds of new techniques, both experimental and theoretical. So people do like a controversy, so they kind of come in. And the experimentalists got into the act. And some clever people, material scientists, managed to design this kind of organic compound with these spin 1 nickel atoms along it, and it turned out to be correct, right? So of course the controversy was very good, and because I was confirmed correct, it was very good for me, because important people who denounced this as nonsense, they had to eventually either say, well, I had to be brilliant or something. Either they were stupid or I was brilliant. So it's a lot easier. But anyway, so anyway, this is an example of now people make up these toy models. Nothing looks more like a toy model than this thing, but then material scientists are managing to make this in nature. And actually, the toy model has been very fruitful in kind of showing up basic physical principles, because you haven't contaminated it with all the actual details of the nickel atom, which is quite complicated, and all this stuff. You've actually reduced something to a cartoon, but that you can actually do a calculation on. And now a lot of material sciences, especially in these attempts to make quantum computing materials, is to actually design the material to go with the theory rather than to make the theory to go with the material, right? So anyway, so again, you see this thing, you can think of this, again, they've got this entanglement thing. If I cut it, there's some connection between the two that has to be broken. And in fact, if I cut the thing, it's like a chain of people holding hands. There's always you'd say, well, if someone's not had an accident, then you know, arms come in pairs, right? But if they're holding hands, somehow those are immobilized, and here's this object with a free arm to flap around on this side and one on the other side, and we'll see at the end that actually some of the ideas in quantum computing are based on something like this material. And furthermore, a bit like a bar magnet, you try to break a bar magnet in two to get a north pole by itself. You can't. When you break it, you get another north-south pair. So if I break the chain here, I can't avoid I will still have a free end at the end of the broken chain, right? And as I say, this turned out to be the simplest of the topological matter states. And on my Nobel, everyone gets a certificate with some watercolor on it, and there's a common theme. So the year we got it, the common theme was the doors opening to a hidden world, and each of us got some different picture, and the one they put on mine was exactly this chain, which actually was not exactly my work. This is a simplification of my work that people after me came up, and it made a much clearer depiction of the state I'd found. It's called the AKLT state. But this state has actually been tremendously influential for people studying essentially entanglement in many ways, right? Okay, yeah, I'll say it was very happy for us that the LIGO people only announced their event after the deadline, because some of the commentary I saw on the scientific press was saying, huh? Who are these guys? Everyone was expecting LIGO to get it. Anyway, whatever. So the second amazing discovery was actually the quantum Hall effect, which was von Klitzing discovered it, and part of the story, or some version of the story, which may be apocryphal, is that he measured a property, electrical conduction property of a system in a very high magnetic field, and found this remarkable result that something called the Hall conductance, a voltage that you can measure across the system, depended only on an integer, a whole number, and fundamental constants. And at low temperatures, a curve which should be a straight line kind of turns into this kind of staircase here. And actually, to do this, it's a function of magnetic field, and this would the resistance. So he was very lucky that he put his device with a constant current flowing through it and switched on the magnetic field. And doing it that way, you actually get exactly the same number showing up on the voltmeter every time you do the experiment. So supposedly he had a digital voltmeter, and he thought there had to be something wrong with the voltmeter because the same thing showed up to so many significant figures it couldn't possibly be true, right? If he'd done the experiment the other way, by sticking the system in a fixed field and switching on the current would never be exactly the same, and the number on the voltmeter would never be exactly the same. And in fact, going back, you could look at people who did a similar experiment in Japan earlier, the other way, and they never saw anything special. So you have to have kind of luck to do things the right way, and then something looked really strange, and it wasn't a broken voltmeter. So there was. And so this is to do with electrons that go in a magnetic field. They're confined to a surface in a semiconductor, and things go around in little circles. But out of this amazing formula, which shows something physical depending on a whole number times really fundamental constants, we now actually have, too bad for the French, who had they had a monopoly on the kilogram, right? We've democratized the kilogram. In principle, if you wanted to check whether the guy in the market had swindled you with using bad weights, you have to confiscate his weights and fly out to Paris and compare them to the weight in the kept in a safe there. And so the only place you could actually do a comparison would be in Paris. But now this, we've actually redefined the fundamental constants to use a balance now called a Kibble balance that uses the quantum Hall effect and also another quantum effect called the Josephson effect to provide a fundamental unit. So the Indian Bureau of Standards can build its own Kibble balance, and it's going to be guaranteed correct, so without having to go to the French and kowtow to Mr. Napoleon who instituted the kilogram. Right? So it started off as a surprise thing, but these things have important consequences, right? So it took some time for the topological nature of all this to become clear. In the magnetic field, electrons go around in little circles. Where's the topological issue? But a system has to have an edge, and the quantum energy of something going around in a circle takes fixed values, Planck's constants times the frequency. But at the edge of the system, they can't go around the full way. They'll kind of collide with the edge. And you can see, actually, if they're going around clockwise in the middle, it'll go bang, bang, bang. It'll bounce around the edge in the anti-clockwise direction. And this is actually an edge state where information at the edge travels only in one direction around the world, which is actually to do with broken time reversal invariance. The magnetic field breaks time reversal invariance that it causes electrons to go around in one way. So if I took a movie of that and showed it backwards, the electrons would be going around the other way, so I could tell if the time reversal was broken. And in fact, this is the electrons in the middle of the thing lie in fixed energies, which are due to the quantization of periodic motion. But at the edge of the system, the electron states go up. There's a special place in electron system because you only put one electron of each type of spin in a state, and the spins are split because of the magnetic field. There's something called the Fermi level, which is the place where the highest occupied state and the lowest empty state are, and that can move freely up and down as I add or remove electrons from the system or change the magnetic field. So that's because of this thing at the edge that allows the thing to give you the same value even if the field doesn't have to be fine-tuned. It gives this topological stability. And so that's very characteristic. And in fact, my co-laureate David Thouless, one of these things, they were trying to understand this. They did a toy model calculation by replacing a kind of system, a dirty system, with a kind of very theorist toy model system, a periodic system where you could do a calculation on. And they discovered this strange formula which showed why the number had to be an integer even if I spread it. And these fellows, about that time, this amazing development called the Berry phase in quantum mechanics was occurring, and as a mathematical physicist heard from some people about this formula that these guys had found, and he learned about this stuff from somebody else, and he just realized, my gosh, this is just Chern's formula for the Gauss-Bonnet-Chern formula. So that's how the abstract formula that Chern had found, version of the donuts and the coffee cups. So, okay, the donut is something abstract here. So around 1988, this is probably the real reason I got this prize, is that this other thing I found was people thought the quantum Hall effect had to really involve magnetic fields, very large magnetic fields. But actually, it can occur, anything with broken time reversal symmetry, which involves magnetism, can occur. So it turned out that you could actually find this quantum Hall effect in much less exotic systems, which are things which, in fact, look like what's now called graphene. In fact, when I wrote this paper, I said, you could realize this in principle in a single layer of graphite, but of course no one will ever be able to make a single layer of graphite. But of course the power of Scotch tape, which led to yet another Nobel Prize, showed you how you could actually peel the graphite layer by layer to get these single graphenes. But anyway, so this gave rise to this. This is a kind of, for those who know anything about semiconductors and band structures, this is a much kind of kinder thing to think about than the high magnetic field systems. And around later, some other people managed to generalize this in another way, change the magnetism of spin orbit coupling, took 2 copies of my model, and now they've got stuff that moves, spin up moves one way around the boundary and spin down around the other. And this is the thing that turned out to have my thing had a very 2-dimensional aspect to it. This turned out to have a 3-dimensional thing. And then this is when people started finding the things in their laboratory shells because they'd never looked for it. So again, this was something no one had expected to find, and it came out of pure kind of theoretical toy model considerations and had a great thing. So it took a long time for all this to be found. So this is actually the example. China has been putting a huge amount of money into condensed matter physics, especially experimental condensed matter physics. And in fact, the people who finally demonstrated my original effect was actually done in Tsinghua, and they got a huge prize in China for this. And it's very interesting because now you don't need the magnetic fields of this thing. You can stick a superconductor on top of it, and there are a lot of very interesting things that can happen with a mixture of superconductors and quantum Hall effect, which is absolutely not possible because high magnetic fields kill superconductors. So we're playing around with a lot of very interesting things with this. So this whole thing about things moving one way, I mean, if you go through Colaba or whatever, they put a little wall along the middle of the road to prevent people playing chicken and going on the other side. But you can see that in a usual wire, the electrons are going in both directions, right? There's more electrons going in one direction to give you a current, but they're all going by actually separating the motion of the carriers, like in a divided highway. You can see it's got possibilities for good things to happen technologically. And in fact, this is actually the same principle. Once you've found physics is very universal, so finding a principle in one branch of physics, you can often find the same principle applies in other areas. So as well as just having this applied to electrons and in materials, it's also you can exhibit the same kind of effect in light. You can make light systems with photonic crystals with this topological structure where light travels in one direction only, and if you put a barrier in the way, the light just kind of crawls around the barrier to keep on going because it can't get reflected backwards. So it's kind of lots of interesting issues there. So actually this stuff went on. A lot of other important discoveries of this came. Probably the most interesting one was the fractional Hall effect, which came after the integer Hall effect. Almost immediately after people sort of decided they understood the integer Hall effect, and the number could only be an integer, it turned out that it was discovered you could also have a fraction, 1/3 rather than, and so this is the famous Laughlin wave function, which he discovered, which encapsulates a lot of the work I'm doing, is really based on staring at this thing. But you can see here, this is the device which they discovered, and this guy made it. There were only 3 people who could get a Nobel Prize, so the theorist who explained it and the 2 experimentalists who measured it got it, but not the guy who made the sample. But actually, see the forgiving nature of topological things. I mean, with this guy, he will not get a job at Intel if his soldering skills are kind of like this, right? So you can see it's a very forgiving device. So what the quantum computing is interesting is this thing called non-abelian states. So this has got even more kind of cool from the fractional quantum Hall effect. So this guy, Kitaev, kind of started a lot of things by pointing out you could use this stuff for quantum computers in principle. And so you do something called braiding. So there's these kind of little defects or vortices in this fluid, and somehow there's information stored in them. I'll come back to that. And so anyway, so this is the heart of the kind of idea of you process the information by moving these things around each other, by not letting them get close. And and the information is actually not stored in where they are, but sort of in the space in between. So this thing is a kind of like a quantum fluid with little vortices in it, and you've got the edge states going one way, and you've got the vortices like a little internal edge where there's stuff going the other way, and you move them around each other. And the key thing in this particular case is that there's 1 qubit for every 2 of these vortices. So there's 4 vortices, but only 2 qubits in the thing. So 2 helpings of information here, and by moving this thing around, I can stir up and change the thing. I think so. Actually, there's only 1 qubit here because there's a sum law that something called fermion parity, that one of them is used up. So essentially, the information is, although you can have a very similar pattern, by looking at where these things are, you can't tell the difference. The 2 states of the system, one with the thing pointing that way, could be the entanglement between those 2. And the state of the system, this Bloch sphere picture, which is I showed at the beginning, pointing the other way, the entanglement is between these guys. And by moving them around each other, you kind of you switch around and move the entanglement around, and that's where the quantum information is hidden. And the thing is, if I take a gun and shoot a hole in it, the information is actually non-locally hidden there, so it's not going to be destroyed by making a hole in this system, because it's not stored at one given point. It's somehow spread out. And you still have to bring these things back together again to measure it, but you can, in principle, do the manipulations by braiding them quite a long time. And so if you actually look at this as an example of the thing there, kind of, if you look closely, these are kind of two quantum states which form this qubit. They look the same. They've got some pattern here, but there's tiny little wiggles which are very small, which get smaller and smaller as I make these things further apart. So if you bring them close together, the information sort of starts to emerge. But when you pull them far apart, you don't see the difference between the little wiggle patterns of those states anymore. So this is actually this is the quantum physicist's beautiful dream of topologically protected qubits, and it's inspired quite a lot of people as one intellectually satisfying answer to the issue of scalability and robustness against incoherence. But of course, you know, the other beautiful dreams that sound good too, right? We heard a discussion this afternoon, the issue of fusion was mentioned as a distant dream, and of course fusion solves the energy problems of the world in a very beautifully, intellectually beautiful way. But the dream of fusion power has been a long time coming, so we'll have to see, you know, how this actually occurs. But actually, I do believe that some aspect of this quantum information thing is going to be a realistic dream, and something is going to come out of it. So actually, Microsoft are the ones who put a lot of money into this topologically protected qubit scheme. And the current platform is something like a 1D superconducting nanowire on a superconducting surface. They haven't managed to achieve the braiding yet, so we'll find out how this actually works. They're behind schedule with achieving braiding, so some people have moved off to Microsoft. I think they might have taken leaves of absence from their universities because, you know, if you don't deliver after a certain amount of time, that's it, right? But anyway, there's a lot of effort, and of course, there's lots of other different approaches. So briefly, the Microsoft approach is based on this superconducting, this nanowire attached to a superconductor, and it's actually, there's a superconductor, there's a wire, there's some business. But if you actually look at how this works as a toy model, it turns out that when you make the electron states interact with a superconductor, they kind of split into 2 parts. And this is this model of Kitaev's. And in some sense, it's a bit like the spins splitting up and then joining hands in a different way. You split the electron states to 2 parts in the superconductor and then rejoin them up in a different way. Now they're entangled, right? And it's a bit like this chain, and now this object, which is the so-called Majorana zero mode, which is now the thing that's left at the end of the chain, which is what is there and the information is stored in the entanglement and things. So it's actually the same kind of very simple pictures that you saw back in the old spin chain thing, this splitting things up and rearranging them in an entangled way and having stuff left over at the ends, which can be interesting. So this is just one of the approaches. There are many other kind of very interesting approaches to quantum computing. There's ion trap qubits, which are probably the best ones so far, but then, to my mind, it's hard to see how that can be scaled to a big device. There's something called superconducting qubits that IBM are doing. There's something called nitrogen vacancy centers in diamonds. There's a whole kind of lots of different people taking lots of different approaches because there's a lot of money being thrown at this problem by governments and companies, and people got excited by this idea of a new quantum revolution. So I actually don't know what's going to emerge, but I'm pretty sure we're going to learn some really interesting things. And finally, so in what I said, there was this thing where different people needed to really collaborate. There's got a toy model builders like myself, but somehow we also needed some mathematical stuff like the Chern integral things. So you have deep mathematical principles, but it's often unclear how to apply them or what they apply to. Very abstract. The toy models are kind of unrealistic, but they give you a thing in principle, and then you actually need the vital people are the people who actually manage to turn all these dreams into some actual material and do a measurement on it, and it kind of makes everything real. And the three communities really kind of communicate with each other. So here's my motivational message to the students. I mean, these discoveries, none of these discoveries were planned, right? I kind of took various random walks and ended up at least a couple of times finding something amazing. So actually, you actually don't need to be a special genius like Einstein. You can be a really special genius and you can do incredibly fantastic work. You've got a huge brain power and everything. But doesn't mean you're lucky enough to discover something that no one knew before, right? You could maybe explain it for everyone, right? But so anyone in science, I think, has the potential a Nobel Prize. Of course, you actually don't go into science to get a Nobel Prize. That'd be pretty stupid because it's a kind of, so the real prize is actually discovering something new, right? Realizing that, wow, this is different from the way people thought it was. So but anyone doing science who's got the time to be able to explore, their curiosity. You see something interesting. Maybe if you have an agenda that's already been set, you have a goal to meet, you maybe don't have the time to investigate it. Well, maybe if it was really cool, someone else will find it later, right? But you do need luck to actually wander into the right area. You need your curiosity to allow you to explore things. And of course, most of the time, things will be kind of a little bit interesting, but won't be, huge. You do need the preparation to actually realize you found something, because if you're walking along the road kicking the rocks, if you're not looking at what you've done, you might not notice that you unearthed a huge big diamond. You just walk on by, right? And usually there's some kind of fight involved in these things, so you actually need some passion in research to keep you going, basically, and not give up when things look bad. But anyway, so actually these are probably the same things you need for success in any business career or anything else. It's the same thing that motivational speakers tell you everywhere. So anyway, so there you go. And finally, as scientists, we do need to try to communicate with the politicians around us and people of influence. I guess I did have a chance to meet Mr. Modi a few days ago, and I had to just. So anyway, this is supposedly me explaining Chern-Simons theory and flux attachment to some influential person. Thank you. Whoops.
Questions?
Hi, good evening. I'm still in high school, so I didn't really get the idea of topological stuff. So in real life, how are such things realized? Like, how do you know what material is in what topological state?
So I didn't catch the question. Topological, well, topological is a fancy mathematical word, but it means, really what it meant was these states can be labeled by something like a whole number, right? And which was something quite unexpected. Usually things can change continuously, and that was the...
Sorry, my question was, if we have a certain material, how do we know what topological state it is in?
You need to have some theoretical, looking for what kind of topological state, but it turned out that actually some of the experiments done here do that. If you look at some of these materials, they have unusual kind of states on the surface, electronic states. Like the examples I showed you had the states in two-dimensional that travel in one direction only. There's something called Dirac cones that occur on surfaces. And in fact, in TFIR, there's people who have the equipment set up to look at the thing. So now we know that a lot of the topological states occur on the surface and can do interesting things. And you can't get, if you break the system in half, you still have the two new surfaces still have it. So once you know it's there, you can go looking for it. I mean, people have the things we use for the quantum computing with these kind of so-called Majorana zero modes. Again, people know theoretically what properties they should have, and they're still trying to. And what you can actually see, you can now see some of these things. For example, some of my colleagues in Princeton, they built a chain of these little magnetic atoms on top of a superconductor, and they can tunnel into it, and they can see the special states at the end, and haven't managed to braid them yet, but these things called Majorana zero modes, which kind of people got very excited about because they relate to something that was predicted in particle physics a long time ago. Still an open question, but so in fact, out of all this stuff has come a lot of unity in physics. Quantum mechanics applies very universally, applies to high energy particle physics and low temperature condensed matter physics. And so people, you need to, of course, have a characterization of this topology, but once you know it, you know what to look for. And of course, there's still new ones to be discovered, yeah.
We have time for maybe one or two more questions.
Good evening, sir. Mm-hmm. So you said that quantum entanglement doesn't exactly... I'm here. Mm-hmm. So you said that quantum entanglement doesn't exactly violate the special theory of relativity.
Yeah.
Can you please elaborate on that?
Well, Einstein worried about the fact if I had this entangled state of electrons or particles or light or whatever that was somehow in a mixed state of being up here and down here and the other one down or down here and up here, or in fact sideways that way and that way, it's the same thing. As long as once you measure it, once you measure this one, you'll always find that the person who measured the other one will find exactly the opposite result if they measured along the same axis. So Einstein felt, how could a measurement made over here change something a long way away instantaneously, right? So he kind of intuitively felt this was crazy, and B, it feels like a violation of the principle that nothing can travel faster than the speed of light. But actually, if you take your laser pointer here and point it at the moon and move your angle quickly, you can make the laser point, you can make the spot on the moon travel faster than the speed of light. But there's nothing actually physical, there's not a physical object on the moon traveling on the faster than the speed of light, and no one on the moon can kind of use that to send a message quickly from here to here. So it's only apparently traveling faster than the speed of light. There's no actual any information traveling that. And so the resolution of Einstein's worry about this thing is that there's actually not possible to transmit any information faster than the speed of light by doing a measurement over here. So yeah, people of course still kind of spend a lot of time worrying about the implications of measurement theory and quantum mechanics, and there's all these kind of ideas, you could read about in popular science about the multiverse, but in the end, okay, those are all fine, but I'm not going to worry about free will and quantum mechanics, but I will worry about whether you can use some of these effects to do interesting technology and science with, right? And so I guess I view myself as a quantum mechanic, not a philosopher.
Good evening, sir. My question to you was that I was not able to understand what is actually quantum Hall effect.
Yeah, the quantum Hall effect is a property of the Hall effect is something to do with electrons moving in a magnetic field. In fact, it's actually the Hall effect is how people know that the charge carriers in a normal metal are actually negatively charged electrons. You can tell by applying a magnetic field. If the current is moving one way, they drift to the left or the right, and you can tell something from that. So it's a property of and the surprising thing in the quantum Hall effect was that you measure this conductivity, which converts a current into a voltage, and you find that it comes out to be this number times these fundamental constants, the charge of the electron and Planck's constant, which is why they've now been set. This has now been defined to be a certain number and set into our system of units. So, I mean, it's a technical thing. The Hall effect was discovered way back in the 1890s, I think, by Edwin Hall, and it's something it's something you'll learn about if you learn about electricity in school, right? So, yeah, it actually tells you that the electrons are carrying the charge in metals.
Yeah, good evening, here on the right.
Okay.
Yeah, so last question. What was the topological property involved in the quantum Hall effect, the fractional quantum Hall effect?
Well, the how to put that in thing. It's actually related to this integral of this Chern number. It's difficult to explain, but in kind of simple terms. But the fractional quantum Hall effect has some interesting stuff happening at the edges, like all these systems. It's got one-way transport, but it's also got very interesting features that the objects, these little vortices inside it, they actually carry a fraction of a charge. In the one-third quantum Hall effect, one-third of a filled level, they carry one-third of a charge. And before, fractional charges came up in the theory of quarks, which is a high-energy thing, but actually you get this property, because of the interesting topological properties of these things, that means they're stable, and they have all kinds of surprising properties. Especially the ones which you want to use for the quantum computing, because there's some extra quantum information associated with little vortices in it. So it's kind of complicated, but basically they're classified. Different possible states they're classified in the same way as counting the number of holes in something in this kind of mathematical language. Yeah.
If there are no further questions, we can thank Professor Haldane again for a wonderful lecture.
Okay. So anyway, if people want photos or something, I got the thing here.